This video is all about acceleration vectors, how to draw them, how to calculate them in component form, and how to extract information about the acceleration vector from a velocity versus time graph. Acceleration has the symbol A with a little vector sign on top of it. That's the symbol you'll see in equations whenever they're referring to acceleration. The units of acceleration are the units of length divided by a unit of time squared. Sometimes you may hear this referred to as something that might not make sense to you right away. So let's think about this. The SI standard unit of acceleration is meters per second squared. Some people might say this as meters per second per second. And I think that way of saying it actually helps you understand what acceleration is better than just saying meters per second squared. So let's look at the description. It says that acceleration is a vector that describes a change in velocity with respect to time. And so the units would be the units of velocity divided by the units of time. And so it's really saying that your velocity is changing by so many meters per second. So it's the rate of change of velocity. And now when we go on and we talk more about acceleration, you'll see some similarities between the relationship between acceleration and velocity compared to the relationship between velocity and position. They're very similar relationships. So a lot of the equations are going to look similar, except in this video, we're talking about the relationship between acceleration and velocity. But a lot of the concepts and the trends that you'll see are exactly the same as the relationship between velocity and position. So let's talk about calculating acceleration, how you could calculate the acceleration vector, either doing it graphically or in component form. It describes a change in velocity with respect to time. So you need information about the velocity vector at the beginning of some time interval and at the end of some time interval. So we'll call this time interval, it starts at Ti and it ends at Tf. So we need to know the velocity vector at the beginning and at the end. So we need VI and VF. The first equation I'll give you for acceleration is to calculate average acceleration. This is when your time interval is some finite amount of time. So you can actually specify when is Ti and when is Tf. And here is the equation that you would use, that the average acceleration is the final velocity minus the initial velocity divided by the final time minus the initial time. So you might write that instead as delta V over delta T, which means change in velocity divided by change in time. And I'll note right now that, remember, delta T is describing a positive time interval because T final always has to be bigger than T initial. Time always marches forwards. We can't go back in time. So this delta T is always going to be a positive scalar quantity. To calculate instantaneous acceleration, you will take the derivative of the velocity vector with respect to time. That's how you could calculate that using calculus. If you remember, velocity is the derivative of position with respect to time. So really that makes acceleration equal to the second derivative of position with respect to time. So these are some equations you may use later on in your physics courses. I want you to be aware of it to understand this relationship, that whatever way you're calculating acceleration, it's always describing a change in a velocity divided by a change in time. The only difference between these two things is that time interval. When you're calculating a derivative, it's for an infinitesimally small period of time. But in the limit, where your time interval becomes infinitesimally small, that means that your average acceleration and your instantaneous acceleration are equal to each other. So let's do an example. I'm going to figure out the direction of the acceleration vector, either one, average or instantaneous, for the two velocity vectors shown below. So I don't really know the delta T. I don't know what this time interval is. It might be infinitesimally small, or it might be, a finite period of time. It doesn't matter. We know what the initial velocity is, and we know what the final velocity is. So here's our two vectors, and we want to figure out the direction of the average, or of the acceleration vector. So recall, I'm going to use this equation up here that says average acceleration is equal to a change in velocity divided by a change in time. Well, a change in velocity is v final minus v initial. So I'm going to take these two vectors and I am going to use graphical vector addition to find this change in velocity. So I'm going to rewrite, I'm going to draw tip to tail vf and negative vi. So I flip the direction of vi and I place it tip to tail with vf. And delta v, the change in velocity, would be the resultant of those two vectors. And so that's my delta v vector written in purple there. That's the direction of the change in velocity. And like I was saying, delta t is always positive. So when I'm trying to get the acceleration vector, I'm taking the change in velocity vector divided by this change in time. Change in time is a positive scalar. And therefore, the acceleration vector must have the exact same direction as the delta v vector, because that time period is always a positive number. So it cannot change the direction of this vector. It's just going to maybe change the length of the vector, but not the direction. So my answer is that the acceleration vector is the same direction as that delta v that I've drawn that's kind of going down and to the left. Before we go, I just want to mention that I'm not going to do an example here. I'm going to record a different video showing a worked out problem using these equations to calculate acceleration in component form. But really, if you know these equations, you can do it graphically, or you can express your vectors in component form and then, subtract them and divide by time and do all of that mathematically in component form. The next thing I wanted to talk about is how to extract information about the acceleration from a velocity versus time graph. So in this case, time is graphed on my x-axis, velocity is graphed on my y-axis. And remember, I only can graph one component of the velocity vector at a time. And so I'm choosing to graph the scalar component of the velocity in x or y or z. And so in this example, I have all three graphs showing the velocity of this object in the x direction, y direction, and z direction as a function of time. And what we want to do is extract some information about the velocity of this object. Let's write the velocity at a particular point in time in component form. And then let's also calculate or obtain the instantaneous acceleration at that same point in time. So I have these graphs here and I want to calculate the velocity vector. So I want to write the velocity vector in component form. So it's going to be some number times x hat plus some number times y hat plus some number times z hat. We can get that information right out of these graphs. So I'm going to focus on t equals 5 seconds, where that graph is at that point in time. So in the x direction, I'd say that the value of the velocity component is about maybe negative 2.5 meters per second. In the y direction, it's definitely at negative 5 meters per second. In the z direction, maybe something around, I'm gonna just kind of guess, maybe around 3 meters per second. So the velocity versus time graphs gives us those exact values, no work involved, just extracting those points from the graph. Now let's figure out the instantaneous acceleration for this object at t equals 5 seconds. So remember, to get that information, we have to consider the slope of the velocity versus time graph, because acceleration describes a change in velocity divided by a change in time. And literally, slope is the change in the y-axis divided by the change in the x-axis. So if I'm graphing velocity on the y and time on the x, this is exactly how I'm going to get acceleration right out of these graphs. All right, so now let's calculate the slope of the graph at these points in time. So at t equals 5 seconds, this first component in the x direction is linear. So I can calculate the slope of this graph at any point in time. I'm going to get the same answer. So I'm just going to choose 2 points off of this graph. I'm going to choose 10 and 5. And this point down here is 0, negative 10. So to calculate the slope, I have 5 minus negative 10 divided by 10 minus 0. And I get 15 over 10. That is 1.5. And my units are meters per second per second. So I'm going to bring that down here into my acceleration vector. I write it as meters per second squared down here. Okay, let's look at the next component in the y direction. This graph is again linear and it's a horizontal line. The slope of a horizontal line is 0. I don't even have to do any math and I can get that one. So the acceleration component in the y direction is 0. Now the last one, I see in this z component graph that the velocity has curvature. So I can't calculate the slope of the graph. What I have to do is draw a tangent line at this exact location. So it's a line that just kind of skims the graph right at t equals 5 seconds. And now I'm going to calculate the slope of this line instead. So I'm going to try to choose as best as I can 2 points from this graph. So I'll choose this one right here, which I said was about 5 and 3. I'm going to go with, I don't really see any other great ones, so I'll just go with this one down here. It's kind of easy. I'll call that 6.5 and 0. So to calculate the slope of that, I have 0 minus 3 divided by 6.5 minus 5. And I get negative 2 meters per second. So I'll bring that down here in my z component. All right, and that's how I can use these velocity versus time graphs to extract instantaneous acceleration without actually doing any calculus. Drawing that tangent line is a little tough, but if you don't know calculus, that's what you're going to have to do instead. The last thing I want to talk about is just kind of conceptually making sure that we understand how to describe the slope of a graph. So in this case, again, I've drawn the scalar component as a function of time, the scalar component of the velocity as a function of time in the x direction. And I just want to kind of verify and make sure that we understand that the slope of the graph is what is giving us acceleration. So I want to categorize these different locations along this curve. Is the slope positive, negative, or 0? So let's look at that. Remember, the slope gives us acceleration. So let's try to figure out where are all the locations where the x component of the acceleration is positive. So on this graph where I'm graphing the x component of velocity, the slope of this graph will give me the x component of the acceleration. So I'm just going to draw tangent lines all along this graph at all of these individual locations. And we are going to consider the slope of these lines. All right, and let's try to figure out, let's see, where do you recognize where you see positive slopes? I see point A, B, and C all have positive slopes. I also see that points I, J, and K also all have positive slopes. Negative slopes, I see those at points E, F, and G. So at those locations, the acceleration is negative. The last one is the locations where the x component of the acceleration is 0. Anywhere I've drawn a horizontal tangent line, that's where the slope would be 0. So that's where the acceleration is 0. And I see that happens at D, H, and L. The last thing I want to do is talk about how the slope is changing. Notice I've drawn a curve. And so the slope is constantly changing. And now I've kind of butchered this curve up into a bunch of different intervals labeled 1 through 6. And I want to investigate where is this slope increasing and where is it decreasing? And I'm specifically talking about the magnitude of the slope. So I don't care whether it's positive or negative, but is the slope getting steeper? That means that it's increasing. Where is the slope getting shallower? That's where it's decreasing. So let's look on the graph and try to find where is it getting steeper. I think in interval 1, it's getting steeper. But then as I get into interval 2, now the slope is kind of leveling off. It's headed towards a plateau at point D. So I would say in interval 2, it's getting shallower. Then it gets to this plateau and then it starts getting steeper again. So interval 3 is it's getting steeper, the magnitude is increasing. Now in interval 4, I'm starting to come back to a plateau. So interval 4, it is decreasing. Interval 5, I'm going back up the hill. So now it's getting steeper. And then I get to a point where it starts to level off again. So I'd say interval 6, it's decreasing. So this is just an exercise to make sure you understand what I mean when I say increasing or decreasing and how the slope is changing. All right, and that's all I really wanted to talk about conceptually about acceleration. Like I said, I'm going to record another video where I'm working out a full problem, doing a bunch of calculations and using math and in component form to actually calculate acceleration vectors.